there may be some groupings already done, or you may have an equation that is not in this form and you expand it out to this form. Either way, the same idea. I mean, here we have this, for example, B complement C complement term. We know everywhere there's just B complement C complement. There's one, so B complement C complement. And for example, then that becomes one group. And you can just go onward. So A, B complement C, there. And then A, B, C, D complement will be there. So we can simplify it a little bit, as you can see, because now we can have this as one huge term and this. Whereas if we compare originally as written, so the original ones were just a grouping there, a grouping there, and a grouping there. So you can see how one of the terms remains the same, this 4-element term. This one has been expanded from 2 elements to 4, and this one from 1 to 2, so there's a slight simplification. The other thing we talked about is how we can convert from different types of gates. So for example, if we're given a schematic with just any old type of gates, we might want it all to be in NAND gates or all to be in NOR gates. The reason comes down to implementation, ease of implementation. Two things. A, if it's all one type of gate, you can just have a huge block of NAND gates that it's then just the interconnections that change. The second reason is that, for example, when we actually create a gate from transistors, the simplest gates to create are NAND and NOR, using only 4 transistors here, or 4 what we'll call FETs. Anything more will require additional logic. So to create an AND gate, for example, we actually would implement an AND gate and then implement an inverter. So the point being that if we can get everything to NAND form, it may result in slightly simpler logic. So that would be an AND. To do this, it's fairly straightforward. The procedure, we just draw the schematic as written. Either if you start with an equation, just draw the schematic from that, or you might just start with a schematic. And we have this list of equivalencies. So let's say we are trying to get 2 all NAND gates. If we're going to NAND gates, we'll only be using stuff that results in potentially useful, so one of these two. And the exact procedure is that we draw the schematic. We first convert any AND gates to NAND gates, and we do that by just adding an inverter on the output, which now makes this a NAND gate. And to compensate, we obviously need to invert something further down, so we add an inverter later on. Then we convert all OR gates to NAND gates, again using that chart from before. So we know an OR gate is equivalent to a NAND gate if we invert both inputs. If you already have an inverted input, as in here, you just add another one. The next step is to cancel those double inversions wherever they may happen. And if required, extract. So here we still have one inverted input. So we need effectively a NOT gate, but we build that out of NAND gates. And then you have a complete design. So you can do the same thing for NOR gates in the exact same way. So the next thing we talked about was the time response of gates. So gates naturally have a bit of delay when something's going through it. So we showed this example before where we have a input waveform in time and an output waveform in time. They're perfectly synchronized. In real life, that's not the case. So before we saw the input change is here at the same time as the output. In real life, the output changes a tiny bit after the input changes. And you can get those values, for example, from data sheets. They show you input-output changes and how much of a delay there is. So the delay isn't constant even for a given gate. It'll vary with, for example, here we see there's actually 2 different numbers depending on the direction, if it's going high to low or low to high. So those result in different times, and it varies hugely with temperature and voltage the gate's operating at even. So here we have an example of some different families of gates, different technologies, and you can see, for example, in this one we're talking around 4 nanoseconds, and this is saying at 25 degrees Celsius. So going in the range of negative 40 Celsius to plus 85, you can see then that it will expand quite a bit. We could be up to 6.5 nanoseconds. Other gate technologies might have even bigger variances. So here's another, the 748C00. We can see from about 7 nanoseconds, typical best case, up to possibly 135 nanoseconds. So this gate delay is a real effect, and we can use it for different things. One thing we can use it for is a pulse shaper, where what I've implemented here would look to be just this function, which we know from Boolean logic would give us 0. But because of the natural delay of the gates, it's not the case. So say we have an input A, and at time here it goes high, and let's just say it stays high for however long, or maybe goes low eventually. Doesn't matter. Say each gate, so this is point A, here, point B, we could say, well, what will happen is that it's the same thing, except it's delayed a tiny bit. So I'll show that delay here. And then goes low. Point C is the same as point B, but again delayed, because the gate adds some delay. And it just goes on. And same thing with point D. So point D is the final input to the AND gate. So then what we have at the output Y is actually basically D ANDed with A. And if we look here, what we'll see is that D is, oh, I forgot the inversion, sorry, so this will actually invert. Let me just clear them. Just redo this quick. We have A, B is the inverted, so it goes low. C is the inverted of that, so it goes high. And finally, D is the inverted of that, so it starts high and then goes low at this point here. So A and D, what we see is they're only both high for this period here. So if I draw that in blue. So the final output, well, we expected it to just be 0 based purely on Boolean algebra, actually results in a little pulse here. So we call it a pulse shaper because for any input pulse longer than this 3 units, it's generating a constant 3-unit pulse. So if we need something that just pulses a light on or pulses something on it.
So if we have delays in the AND gate?
So there would be delay in the AND gate as well. I don't consider it here. Effectively, the delay from each point will almost be the same, is what we're considering. So what this would do is just shift the whole thing over a tiny bit. So then really point Y would look something like, this in reality. Because again, we have that same type of delay. So that's a good point actually. But this width is still the same as before, just shifted. So another use for them we'll show is the ring oscillator. So the ring oscillator, we use an odd number of gates together, and it again takes advantage of this delay. So if we start with say 0 here, what you expect to happen is 0, 1, 0. And the output's 1, which doesn't make sense because it's almost shorted backwards. In reality, though, because of the delays, the output Y ends up being a square wave like this. And why that is you can just start some arbitrary input. Say A is 1, and then goes to 0. At point B, again, we have an inverter, so it starts low and then goes high. Point C, we're saying it starts at this point, goes low. And point D, here. So what you notice is point D now feeds back to A. So in A, I had said, well, it's low. At this point, because D is driving A, it forces A high. And then this whole process repeats. And then there's a delay before the output D changes, feeds back to A, changes, delay, changes, etc. So this will result in a square wave output. And the more gate delay you add, the longer this period becomes. And then the lower the frequency will be. Yep. So power, the gates themselves have power. So it's not shown here, but they, yeah, so there's, VCC and ground. So if you want to think, about physically how it's done, let me see if I have a blank. I'll use this. When we build a NOT gate, what we have is again, these are FETs, so you can just think of them like switches. We have this, and then VCC, which wasn't shown, is here, and so ground is here. And then we just, again, draw this quick. And these all connect together. Okay. Yeah, so and then you have a third one and the output. No. So it's just, with the gates, all that we really consider being transmitted is just a signal level. So we almost don't think about power contained within it. And then, so all the power for this whole circuit is coming from this rail here. So this VCC, which would be 5 volts or 3 volts or whatever we have. Make sense? So the downside of gate delays are some not so useful side effects, and we call these glitches. And that's where, for example, if we have this circuit, we expect, for example, going from 0 to 1, the output to stay at some state, which I think we expect it to go from 1 to 1, basically. We expect it not to matter. But what might happen is the output actually goes from 1 and then for a very brief time to 0 before going back to 1. So it actually looks something like that. And this is a tiny, tiny little pulse that just goes down. And we call that a glitch because it's not supposed to happen. The glitches are a problem because the circuit could be connected downstream to other stuff. Like you could connect it to an alarm, detonator, or something like that. This little glitch could cause an unintended effect in the grand scheme. So we don't want that. And the glitches come about because you can think, for example, that when this transition happens from 0 to 1, it's effectively instantaneously put to the input here. But on this leg, it's not instantaneously put. So there's a delay here. So the old value will actually still be there. So the 0 or the 1 would still be here when it should be going to 0. And that's still 1. So in this circuit, it might not create a glitch, but the point is because we actually have two values within the circuit for a very, very short period of time, it can create this glitch. So we call it a hazard because there's a potential for a glitch. We may have static 1 hazards where the circuit is supposed to be 1, glitches to 0. Static 0 hazards where it's supposed to be 0, glitches to 1. And dynamic hazards where it changes a few times. We only consider a single bit input change, so one variable changes a tiny bit. We don't consider multiple bits changing to create a hazard, so just one single bit changes results in this glitch. To find hazards in a circuit, to see if it's hazard-free or not, what we do is we can look at the K-map. So within the K-map, we can draw, so for example, say I have this circuit, we can say, okay, A and B is this term here, and then B complement C is this term here. And within each of these terms, the output is 1. And when we created the K-map, we went through the truth table, whatever, it's 1. And the problem is when the input switches such that the 1 is created by this term here, this product term, and then the input will change so that it's created, the 1 is created by this product term. And what happens is that in the intermediate time here, you can sort of think about it this way, that it's not covered by either product term. And that's bad because that means it may go to an unintended value. It's not forced to something specific. So to fix that, we just have to create a hazard form that always encompasses the whole, all transitions. So we draw another product term around those two. This we could call the hazard-free form now. So this additional product term does add extra logic. So we could say, for example, it's A and C. So the hazard-free form becomes A and C. And now we have the hazard-free form of the circuit. So to find hazards, we just look at the product terms and try to find locations like that where there's two that aren't covered. So there's sort of a adjacent bit of gap. And then you can implement the circuit there as such. If we do this process and it's a two-level network, then we can say that removal of those hazards, so with finding the ones in the adjacent product terms, removes other possible hazards too. So for all we care about, you can just do that process and call it a day. Multi-level hazards are where our original circuit, or if you can sort of look at the equation, might be written in such a form that we have many levels of gate logic. So, maybe something like that. So the problem is that different elements could be delayed by different amounts of time. So we might have, for example, this input here. When this input changes, it'll instantaneously go to this gate, and it'll also have 2 unit delays because it will go through this gate delay and then this gate delay and then arrive at the input. But other inputs, for example, if this input, it'll only have 1 gate unit delay. So when we have multi-level hazards, this is where we get the dynamic because it could change a few times. So to fix them, all we do is we basically take the equation we're given of the circuit and reduce it down to a 2-level form. And then we do the same process and you're done. When you're doing this, don't use the complement laws or many of the simplification laws that have been derived from it. So basically, for the most part, what you can do is use the distributive laws to find it. So for example, we went through this in more detail yesterday, but if I have this form, so this is a multi-level form because we can see we have an OR followed by an AND followed by the whole thing OR. We just distribute, so A and A complement plus A and C complement plus D, etc. And now we have a 2-level form, and we just leave it as that, even though normally what we would have done is simplified some of those terms. And then we can map it. So do this in red. So for example, ABC, again, this is just like all of the K-map stuff we've been doing. That's ABC and A complement we don't use. A and C complement. These. D and A complement. Oops. Down here. And then D and C complement is, where's that one? So it's this. So what you can see is that there's a few potentials for hazards in this circuit. So we can see we have a transition here, we have a transition here, and I thought there was one more. No? Okay, well, so to fix it, what we could do is, for example, if you make a term here that encompasses everything, and maybe a term here. So we've added 2 extra product terms, and those encompass those sort of jumps. So again, it's the same process. When we want to select product terms, you want them to encompass as many as possible. So although I could have here just done 2, 2 this way, 2 that way, it's better